Yeah, I'm recording. So today we have Dr. Niccolò Cribiori from KU Leuven to talk about scale separation from backward rolling solution. Welcome.
Okay. Thank you, first of all, for the invitation, and I hope to be able also to be there in person soon. So this talk will be about a topic which is wide, so we'll not for sure cover all of it. And I will review, in the first part of the talk, I will review what I think is the current state of the art of the topic, at least to my knowledge. And then in the second part, I will give two recent developments in which I was involved together with other people that I will mention on the way. Okay, so the problem is scale separation. And to understand this problem, I would like to start from really basic facts about our universe and the length scales we see in our universe. I will be not very precise with numbers, but for basically all of the talk, I will just work at the level of orders of magnitudes. So for sure, in our universe, we see some background dark energy density, which is positive and very small. And if you want to convert into meters, it's some 10 to the minus 4, more or less, as order of magnitude. On the other hand, we think there is a fundamental length in nature, which comes out from combining together fundamental constants like h bar, the velocity of light in the vacuum, and the Newton gravitational constant. This is the Planck scale. And this very, very small in meters is some 10 to the minus 35. Then whenever we have lengths, we'd like to compare them. And from this comparison, we see that we have a very small number, which is 10 to the minus 31, is a pure number. And as physicists, we would like to explain, whenever we have these small numbers in theories, we would like to explain them from fundamental principles. Another very similar, actually, problem can be formulated by looking at the size of the observable universe, which is some 10 to the 27 meters. So it's huge, but finite as far as we know. And on the other hand, the size of the would-be extra dimensions, it's much harder to estimate because we don't observe them, so we can just put upper bounds. And the magnitude of these upper bounds is really depending on which kind of reasonings and experiments we are using to probe them. So if we say that we don't see any evidence of extra dimensions in particle physics or in colliders, we may want to say that for sure they have to be smaller than the inverse energies probed in the colliders in terms of a length. And this is some 10 to the minus 18 meters if we use LHC. But it's not the only way. For example, if you are interested in gravitational interaction and you want to use bounds from torsion balance experiments, then the numbers are a bit less dramatic. It's some 10 to the minus 5 meters. So this is something which, in principle, it's even observable. It's not microscopic, I would say. It's micron scale or more or less. Anyway, now we face a similar problem of having a small number because on the other side, we have a very large number, which is the size of the universe. So again, if we compare them, no matter which number you use here, you are ending up with having a very, very small number. And these kind of small numbers are more precisely called hierarchy problems. And scale separation is indeed kind of an hierarchy problem. It's indeed the problem of explaining is this second kind of problem, but it's, I think, very much likely related to the first one. And it's the problem of explaining why we don't observe extra dimensions to very, very small scales. This problem might not be severe if you start or if you believe that for some reason there should not be extra dimensions, but if we would like to study quantum gravity, and if we believe that string theory is today the most developed approach to quantum gravity, then string theory is best understood as a theory with extra space-time dimensions. Therefore, there is a problem we have to face whenever we are trying to study quantum gravity via string theory, or even more trying to connect string theory to observations. In this framework, the most studied approach, which is not the only one, but is the most developed today, it's called compactification. So it's the idea that the full 10-dimensional space in which we understand string theory, it's actually split into two parts. One is the external 4-dimensional part, the one which we live. And then there is an internal 6-dimensional part, which has to be likely very, very small. What I need for this talk is that this process of a compactification is generating a new scale, which is the compactification scale, or I will call it the Kaluza-Klein scale. And then we can reformulate the comparison between within the external and the internal universe as a comparison of length scales. And then scale separation is the requirement that the Kaluza-Klein scale over the length of the observed universe is very, very small. We don't know how much small it is, so for this talk, I will just ask the question about parametrically small. I cannot be more precise than this. So scale separation means being able from string theory to achieve this kind of hierarchy. And as I was saying, this is really important. I think it's a necessary question to connect string theory to observation. You cannot avoid it, I think. It's a basic question. It's like one of the first things everyone would think about string theory when trying to connect to observation, but still it's an open problem. We don't have like a clean solution for this problem. And let me stress that if it turns out maybe in a few years or more that this hierarchy is impossible to achieve in string theory, it is not, I think, the end even of string theory of this kind of research, because it just means that this is not the way to go. There are other options to connect string theory to observations, which are not going through a compactification. So it just means that we are doing the wrong approach. And even in this case, so we would learn something. Okay, so the first part of the talk, then I will concentrate on reviewing the problem of scale separation in the most studied setup, which is the one of vacua, so minima of a scalar potential. And really, we are trying to understand the problem in the most simple settings, which are not realistic. So we are not trying to solve both kind of hierarchy problem, the ones I was mentioning at the beginning. So we are not trying to implement scale separation on a background with positive energy density, because we would need also to break supersymmetry in the meantime, which is yet another big open problem. So we are trying to understand scale separation in unrealistic setups, which are anti-de Sitter spaces. And they come with a length scale, which I will call LADS. And then the requirement is that we would like to have solutions of the equations of motion of string theory in which we are able to achieve this hierarchy. And on top of this, we need also another hierarchy here because of the way we derive these solutions. So these solutions are derived via the supergravity approximation to string theory, which is somehow the classical limit of the theory. And so we have to be sure that the string correction we are neglecting are safely neglectable. So this hierarchy is there to implement that regime. Now, let me then review what has been done in the past roughly 20 years, more or less. So here I'm plotting the theory space. So here there is the number of external space-time dimensions of the anti-de Sitter vacuum. In this case, so there will be a 2-dimensional anti-de Sitter, 3-dimensional anti-de Sitter, 4-dimensional. So this is the line we are mostly interested in, probably for phenomenology. But as a theoretical question, I can go up until 9, I think. And then, as I was saying, I need supersymmetry to have control over my computations. And it's a fact that we cannot construct any amount of supersymmetry in any arbitrary dimension, because the number of supercharges depends on the number of space-time dimensions, because the way fermions behave changes with the number of space-time dimensions. So there is a region which is already excluded just for supersymmetry. I cannot construct supersymmetry representations in this area. For example, in 4 dimensions, the minimal spinor has 4 components. So the minimal supersymmetric theory has 4 supercharges, it's called n equal 1 supergravity. I cannot go below. So I can be non-supersymmetric, so 0 supersymmetry, but I cannot be with 2 supercharges. And then there is a similar logic for other dimensions and other supercharges. So this part of the theory space is excluded for whatever question you're asking. Just there is no model here besides scale separation. But here, in principle, anything can go. Here we have to really see what happens. Now, until 2005, the story was pretty much this. There was one model studied by many people until 2005. I'm here reporting the names of the authors which made this paper today famous. It's called DGKT after these authors, but other people around that time found this class of models. And it's a model with a four-dimensional n equal 1 anti-de Sitter vacuum, which comes from compactification of massive type 2A supergravity, and I will review it a bit later on also. But it's just a single dot here. And from 2005 and 2020, basically there was no progress in finding new models. So all of this possibility remained unknown. There could be a model somewhere here, or there could not be. We just didn't know. This question was not investigated. And of course, the same will apply for the non-supersymmetric vacua. I will not discuss them, basically because we have typically less control over the constructions. And but keep in mind that every time you see a dot here, there will be a cousin below here. So this kind of solution come with a property such that if you flip some signs in some fields, like Ramon-Ammon fluxes typically, you find a very similar vacuum which just breaks supersymmetry on top of the other property. So you will keep scale separation, but you will break supersymmetry. So every dot here, for every field dot here, there is a cousin here, but just one instance of a model. There can be many more that we just don't know. Okay, then in 1 year, from 2020 to 2021, new models have been found, in particular another one in 4 dimensions that I will mention later on. And this was the first ever model at strong coupling also, so which possibly could be understood from an M-theory's perspective. M-theory is this non-perturbative completion of string theory. And another new model in 3 dimensions. Then, again, a few years later, from 2022 to 2023, we understood how to give obstructions to scale separation, okay? So instead of finding models, another possible strategy is to try to exclude regions of perimeter space by means of some principles or assumptions. And I will briefly review also some of this. And here we understood that if you believe in a property which is called the weak gravity conjecture, which is a well-tested property, at least in Minkowski. So in Minkowski, I think it's widely believed to be true. In anti-de Sitter is a bit more speculative, probably, but let's say some version of it should be applicable in anti-de Sitter. Then you are able to exclude large portions. So basically, all theory with large amount of supersymmetries from 4 dimensions and up to 9 dimensions are likely not to give scale-separated anti-de Sitter vacua with supersymmetry. This is the statement. So here we believe that it should not be possible to find scale-separated vacua unless you violate with the weak gravity conjecture. Again, a few years later, until today, we understood also how to rule out models in 2 dimensions. 2 dimensions is a bit trickier because, like properties of quantum gravity, which we believe to be true, like the weak gravity conjecture, famously in 2 dimensions, you have to be much more careful because 2-dimensional gravity is quantitatively different and qualitatively different than 4-dimensional or higher dimensional gravity. So you cannot really use them as you would use these properties in 4 or higher dimensions. So you have to come out with alternative strategies. So it's a bit more tricky. We think we found a possible argument to exclude all supersymmetric to exclude the scale separation in all supersymmetric anti-de Sitter vacua with at least 2 supercharges in 2 dimensions. And also new models recently were found again in 3 dimensions. So 3 dimensions is actually a very rich setup. So the situation is then that in a bit more than 5 years, this was the progress. We started from one model, and today we know that most likely the situation looks like this. In 4 dimensions, we probably have singled out already the unique corner of the parameter space in which it's most likely to find scale separation. We believe that other corners are not possible. 3 dimensions is very much open instead. and 2 dimension, there is a spot which can possibly host scale separation. We just don't know. There might be, or there might not be. We don't know yet. So we understood then in 6 years that actually scale separation is not generic because we excluded the vast majority of the parameter space, and independently the new vacua that were found were arising in those corners which are not excluded. So these are like, I think it's an important self-consistency check of both kind of approaches. And let me stress that whenever you see an X, as I was saying before, it means that these geometries are most likely not scale separated anti-de Sitter geometries, but it doesn't mean that there is no anti-de Sitter vacuum. We know that like ADS5 process 5 or other ADS7 process 4, we know this vacuum exists. It's just that they are not scale separated. Okay, I'm just asking the question about scale separation. In this ADS5 process 5, famously the size of the ADS part is the same as the S5 part. And so whenever you will find an ADS, I don't know, 6 vacuum, it's very, very likely we believe that the compact space will be of the same size as the ADS part. Okay, this is the kind of information you gain from this table. And to be even more careful, whenever you find a dot, it doesn't mean victory, okay? Because this dot really means that it's likely that there can be a model with scale separation. There are concrete proposals. But to find these models today, since we don't understand string theory in full detail, we have to make assumptions. And then the quality of that model really depends on the quality of those assumptions. So the research today, even in the very first model that was found, is still active and actively trying to improve on those assumptions. I will mention some of these assumptions later on. So you have to be careful in interpreting these dots as well, and we have to be open-minded. Maybe there is also the possibility that none of these dots will survive a much more improved scrutiny. We don't know, but these dots today are the most likely points in parameter space where to find scale-separated vacua in anti-de Sitter at least. Okay, so let me then review briefly how this research is done with concrete models. I will review, first of all, the very first model, what is called DGKT. I will be schematic, not give you the full details of the model, but just to give you the logic in which we try to construct these models. And then I will review the other model at strong coupling. So as I was saying, the problem is to find scale separation in the Sitter, and the problem is that there is no preferred strategy, okay? You have to somehow be lucky in a sense to that you can really end up in a vacuum which has this property. What we do today is try to find for models which obey this relation. So there is a one parameter family of vacua. For example, in the S5 process 5, we have this parameter N, which can tune arbitrarily large. And for DGKT is the same. There is a parameter, which is a flux charge here. There is a four-form Ramon flux. This flux is such that it doesn't enter other constraints, other Bianchi identities. So typically you have equations of motion and Bianchi identities to solve. And Bianchi identities are kind of constraints on the amount of fluxes and charges you can have. It happens in this model that F4 drops out. It's just a mathematical fact, meaning that we believe it's possible to take arbitrarily large amount of this charge. And then we have one parameter family of vacua, and that's already remarkable. But what is more remarkable is that these vacua are such that the ratio between the Kaluza-Klein scale and the ADS radius is also depending on n in a way that it goes down to 0 when n is large. Okay, there is an exponent which you can calculate. I'm not sure. Yes, I'm giving it here. It's 1/2. So this ratio goes to 0 the more F-form flux you put. And in general, we would like to find models which have this general property. Maybe alpha is not 1/2 like here, but these the kind of models we are looking at. So I already anticipated a bit of the details. So there is one unbounded flux, and then there's a model, a compactification of type 2A on a Calabi-Yau manifold, but the best understood setup is like the toroidal orbifold underlying it. So we have a T6 torus. You can think of it like a product of two tori, which are drawn here. And in the simplest case, you can take them to be all of the same size. And you can check that on the solution, this size will grow with some power of n. And this size will grow with some power of n. And you can check this also, which is the power of n under which all the other quantities are growing, or all the other length scales are growing. The ADS scale will grow with some other power 3/4. The Kaluza-Klein scale with power 1/4. And also another important quantity is the string coupling, because it's the parameter controlling string loop corrections. And you want basically this number to be small in your solution, because in this case you can be more certain that the supergravity approximation you're using is consistent. And in this model, the powers of n are all working in the correct direction, such a way that when you take n large, you have small string coupling, a very large ADS space, and a Kaluza-Klein scale, which is large but is growing less fast than the ADS radius. So when you take the ratio, the ADS radius is growing much faster, and then in this way you realize scale separation. This is probably the simplest model in 4 dimensions we have today. Let me give you a new, okay, it's not new anymore, now it's 5 years old, but DigiKT is like 20 years old, I would say, so it's newer than the previous one. And okay, the way we found this model is by reasoning in terms of T-dualities from DigiKT, but you can also just be lucky and guess it from directly. So DigiKT, the model I reviewed before, is a model in massive tapped wave. It's a deformation of the standard tapped wave with the Roma's mass. And one property of this theory, which is known, is that at the supergravity level, is not clear how to uplift the theory to 11 dimensions because of the Roma's mass. On the other hand, if you are in massless tapped wave, so the standard tapped wave theory without the Roma's mass deformation, it is known in principle how to uplift the theory to 11 dimensions, so to the classical limit of M theory. This new model is in massless tapped wave. It's a bit more complicated. So again, we can think of this like as a toroidal orbifold with a bit more structure, but okay, I will not enter the details. But now, crucially, the toroidal orbifold cannot be isotropic. There are 3 tori, but they must be of different sizes, otherwise you don't realize scale separation. So this model was in fact known before our work, but it was not known to be scale separated because people usually at the beginning, they study the isotropic case. And then therefore they missed the property of this model that it could realize scale separation. What part of our work was really to understand that going into the non-isotropic case, you can get much more interesting vacua. So this means in practice that there are now 3 unbounded charges, Q1, Q2, and Q3, which are integrals of different fluxes, and 3 different lengths for the 3 tori. And then you can just do a scaling analysis. Here I'm already reporting the results. There are 3 arbitrary parameters, A, B, and C. And here I'm reporting how the ADS scales with these parameters and with the power of n here, the KK scale, and the string coupling. And you can take the ratio, and you see that if B is positive, which has to be because of flux quantization, then this ratio is going to 0. But you can put any value of B you like, actually. So it's a larger class of models than the one I showed you before. And in fact, you can ask also, since now you have freedom here, you can ask when the string coupling is increasing or decreasing. So when you're going to strong coupling or weak coupling. Now, going to strong coupling in massive tapped wave, it's, as I was saying, is not understood because we cannot uplift to 11 dimensions. In this case, we have this hope that when we go to strong coupling in massless tapped wave, we can uplift to 11 dimensions and reformulate the problem in an M theory language, which could possibly lead us to a better understanding. So this is a reason why we also study the strong coupling case in this case. And there are 2 branches depending on this inequality. Whenever B plus C is bigger than A over 3, we are a weak coupling, but we can also take the opposite regime and then we are a strong coupling. So what this is pointing us is the solution, the existence of weakly coupled massless tapped wave solutions with scale separation on the one hand, and also the possible existence of strongly coupled solution with scale separation. So it means possible existence of M-theory solution with scale separation, which deserve further investigation. Okay, this is the way we try to construct the models, but also let me review briefly how we can give arguments to forbid the presence of scale separation. I mentioned at the beginning the weak gravity conjecture, which is the statement that in the way I will use it, at least, it's the magnetic version of the weak gravity conjecture that is an electric and a magnetic version. The way I will use it is the statement that minimally charged monopole should not be a black hole. Basically, this implies that there is an upper bound of the ultraviolet cutoff of my effective field theory, which is given by the gauge coupling in Planck units. Now, in dimensions greater or equal to 4, whenever I'm doing supergravity, I know that the anti-de Sitter scale is set by a parameter, an important parameter in the theory, which is the gravitational mass. This statement is true in any kind of dimensions and any number of preserved supersymmetries. Now, if I have enough supersymmetry, it means at least 8 supercharges, so n equal to 2 supergravity in 4 dimensions or higher. I'm able to trade the gravitational mass for gauge couplings. Okay, this is a property of supersymmetry which I'm not able to do in general with less supercharges. I might be able in some specific cases, but not in full generality. So it means that basically the ADS scale is set by some gauge coupling with some appropriate Planck masses. And this is really the kind of quantity that enters the magnetic formulation of the weak gravity conjecture, which is the statement that this quantity is upper bounding the ultraviolet cutoff of the effective field theory. And then, since we are doing supergravity, I think a natural cutoff will be the KK scale. So we can write down schematically this inequality. Actually, the full computation is highly non-trivial because you have to work with spatial geometry if you do n equal to 2, for example. So I'm here sketching the logic. But from the first part here and the last part here, you see that this ratio is actually lower bounded by 1. So you want this to be parametrically small to have scale separation, but here you are really in the opposite regime. So this kind of these combinations of supersymmetry and weak gravity conjecture, it's pointing towards the impossibility of having scale separation. In 2 dimensions, it's a bit more tricky, as I was saying, but we believe we have a possible argument, which is more recent, is from 2 years ago. So here I have the argument in general dimensions, which is similar to this one, but let me also repeat it because I will present it also later on in a bit more detail. Again, we start from the vacuum energy, which is the ADS scale. And then now, instead of the weak gravity conjecture, we assume that the ADS vacua we are looking at are interpolated by domain walls, okay? If this is a natural assumption, if you think there is like a landscape of vacua, and you can pass from one to another via domain wall transitions, but we don't have a proof that this is a general case, okay? So this proof works, this argument that I'm presenting works under this assumption that there exists an interpolating domain wall between any 2 vacua, and this domain wall must be BPS for the argument to be run. Otherwise, again, I cannot have a general argument. It means that, so under this assumption that the existence of a BPS domain wall, you can trade the vacuum energy for the tension of the domain wall. There is an index step, which is trading the vacuum energy for the charge of the domain wall, but then if the domain wall is BPS, the charge is equal to the tension, and you arrive here. Now you ask another assumption that the domain wall is fundamental. It means it cannot be resolved by your effective field theory. It means that you cannot see the degrees of freedom on top of the domain wall. Effectively means that the tension of the guy is giving an upper bound on the ultraviolet cutoff of the theory. And then, okay, you repeat a similar logic. You upper bound the cutoff with the KK scale, lower bound the cutoff with the KK scale. And now you arrive at a relation of this kind. For generic dimensions, this is not telling us much, even though we'll come back later. But you see that if you put it equal to, this ratio disappears, which is consistent because there is no Planck mass in 2 dimensions. And you end up again with the same inequality that you see here. We are completely different reasoning, but the result is the same. So these are reasons why we believe it's hard to construct scale-separated vacua in 2 dimensions. At least this kind of vacua will be interpolated by BPS domain walls. If they exist, they should not be scale-separated. Okay, now let me say a bit more about this last part about domain walls and scale separation. These are recent series of work I've done with several people. I would like to point out a possible connection with another subject in principle, which are entropy bounds. But we found that this kind of reasonings in terms of domain walls seems to be related to entropy, and they all seem to have something to say about scale separation. So what are people typically doing very basic way with entropy bounds? So you consider a system like a box with n weakly interacting particles, and you know that the entropy will scale extensively. It means with the volume of the box, which we can parameterize in terms of the size and the ultraviolet cutoff. And extensively means there is d minus 1 power here, okay? It's the spatial area, let's say, volume. Asking that the box is not a black hole gives a bound, which is famous, I think, in the literature, even not so much in the string phenomenology literature, but this paper is highly cited. And this bound looks like this. Actually, this is a very severe bound, and we don't have like a first principles derivation of this bound from string theory. But still, this is a very well-known bound, I would say, in a past part of the bibliography, part of the literature. However, less severe requirement is the bound that is requiring that the entropy should be upper bounded by the entropy of a black hole of the same size. This is like what is called the Bekenstein bound or the Boso bound, the covariant entropy bound in more fancy constructions, which amounts to an inequality, an upper bound on the ultraviolet cutoff in terms of the infrared cutoff. And here I put the Planck mass to 1. If you restore the Planck mass, you actually end up precisely with an inequality of this kind, more or less. And I will show now the logic. So what we have done in the recent years is to, first of all, to put on more solid grounds this kind of bound in the sense that we can derive it from the supergravity equations of motion in 10 dimensions, and then we ask what are the consequences in proposed vacua with scale separation. So how does it works? How can we derive an upper bound on the ultraviolet cutoff via the equations of motion? And this is where domain wall will enter. So again, I'm interested in vacua which are anti-de Sitter. The equations of motion from 10-dimensional supergravity in some approximations, for example, we take the scalar fields to be constant, looks like this. So here are the traced equation. The vacuum energy, the Ricci scalar, which is the ADS scale, is sustained by fluxes with possible legs, various legs, and the possible presence of sources, which are parameterized by delta functions in the equation of motion. Typically, in the typical situation like in the GKT, this is a sum of terms, but they are all of the same size. Sometimes this is called the tile balance condition. So you can typically write an inequality of this kind from some order 1 number, which depends on the details of the vacuum. And then once you are here, so once you know that the ADS scale is upper bounded by the flux square, you use domain walls in the way I used before. So you know that flux squares means charge square. And if there is a domain wall, which is BPS, it means tension square. And then you ask that the tension is upper bounded the UV cutoff, and you are done. Basically, you found the same relation I was mentioning before. Now, from a more fundamental theory, I would say, which is 10-dimensional supergravity. And this is a recent work which appeared like the beginning of the month. We call it domain wall bound because it's because of the role that domain walls have in this discussion. And then once we have this bound, we would like to test it for models against models with possibly realized scale separation. So we find that classical vacua like DGKT and the other vacuum I showed you before with scale separation, they all satisfied it, both in 3D and 4D. Whenever you go beyond classical vacua, however, the situation becomes more interesting. For example, I didn't mention it, but there is a very well-studied proposal for a de Sitter vacuum non-instant theory, which is called KKLT. And among the other properties, to realize it, you have to achieve an ADS vacuum with scale separation, with a certain degree of scale separation. And so this is a scenario which was proposed a long time ago, and today the most developed construction in this sense was essentially built by a group in Cornell in this series of works, and they propose anti-de Sitter vacua with huge amount of scale separation. So these are the lengths, the ADS lengths in Planck units, for example. You see that there are really huge numbers. And then we just test this kind of bound against this vacua, and what we find is that this bound is parametrically always violated. Because to be satisfied, this column should be less than 1, but you see that it's parametrically larger than 1. So we believe that there is something to be understood better about these EFTs, and one possibility is that these EFTs are not including the degrees of freedom of the domain 1. Another scenario I will just mention in case you have heard about it, otherwise it's not relevant for the rest of the talk, is called the dark dimension scenario. Is a new proposal to assess the cosmological constant problem, and it predicts the existence of a fifth space-time dimension of micron size. And then we test this bound against this scenario, and we see that, so this is a scenario, we don't have concrete models. It's like, while these are concrete models, here we don't have the analogous. So it really is more heuristic, the analysis. We have to distinguish also what we are doing. If we take the ultraviolet cutoff to be the 5-dimensional Planck scale, then the bound is violated. If we take the Kaluza-Klein scale, it's satisfied. So we don't know yet what is the fate of this kind of scenario with respect to the bound I showed you before. Okay, so to summarize, scale separation on vacua, supersymmetric vacua I talked about, seems to be not generic. But then if we really believe that scale separation is the way to go, we have to be more creative. And one possibility is that maybe we are too restrictive in looking for vacua. So as a theoretical question, what happens when we try to go away from vacua for the problem of scale separation? And in any case, there is no evidence that we live in a vacuum today. So what we measure is a background energy density, but we don't know if it is a cosmological constant or it's slowly varying. Both possibilities are still open experimentally. So we as theorists, we have to be open-minded, I would say. So from my perspective, more down-to-earth perspective, one interesting point of study this kind of question is that we bypass no-go theorems for against scale separation in a way that was not known before. So the problem of scale separation is studied a lot, and there are even other no-go theorems I didn't mention, but I will mention in a while, that are telling us how you most likely will not find scale separation, similarly to the way I was using the weak gravity conjecture, albeit in a bit a different way. It turns out that these theorems, especially this one, assumes a vacuum solution. It means that you can evade it by going outside vacua. Okay, so this is the second part of the talk then, in which I will talk about scale separation on rolling solution, but let me stress that I will be less explicit, because this is like, at least in my understanding, we are just starting now addressing these kind of questions. We don't have very explicit models like DGKT or the other models I was showing you before, but I think it's important to start asking these questions also in view of data from cosmology. Okay, so first of all, why it is hard to achieve scale separation? Again, let me give you another hint that scale separation is an hard problem from a string theory point of view. Now let's consider compactification of type 2 string theory to 4 dimensions. It will generate a scalar potential which depends on the various ingredients. You have Ramon fluxes of various degree, H flux, D branes of some 3 plus k dimensions, 3 because I want them to be space-time filling in the external space, otherwise I break the isometries. And then there will be also possible terms from the curvature of the internal space. Now, if you assume that this guys are positive, meaning you have d-branes and not negative tensions objects like O-planes, like orientifals. You assume that you cannot decouple the Kaluza-Klein scale from the scale of the curvature of the internal space. This seems a bit a weird assumption, but it turns out that is hard to evade. For some reasons we don't understand, most of the manifolds have this property. And you also assume that you're on a vacuum solution, so you can use this kind of information. Then it's very simple actually to calculate this ratio. And you see that this is upper bounded by 9/2, basically. So you have some parameters, P and K, to put inside. But under these assumptions, this guy can at most be 9/2. And this means there is no scale separation under this assumption because these are basically the same scale. Now, there are ways out, of course, because we have proposals for scale-separated vacua that I already discussed. One, the most famous one, is adding negative tensions objects. So you don't just have d-branes, but you have O-planes, for example. And indeed, like DGKT has O-planes, all the other models I discussed before, they all have O-planes. You can relax this second assumption, but as I was saying, it's a bit harder. The only model I'm aware of that does it is this model, so the model at strong coupling, even though we don't really understand why. So we didn't know, when we constructed the model, we didn't know it was evading this thing. We just found the scale separated solution, and a posteriori we checked and we saw that this was happening, but we don't have an explanation. But third is the third way to bypass this obstruction is to go outside vacua. So you relax this. So if you relax this, you cannot write this inequality anymore. And this is what we explored. Sorry, there is a typo. This last year, 2025. In this paper last year. So this is motivating theoretically from string theory, and for people who are looking for string theory solution, is motivating why we would like also to go beyond vacua. I will give you essentially two examples, because also in the paper we don't have much more. Again, there is a typo, sorry. We don't have much more. It's like a preliminary investigation, I would say. But I think they are very simple, but I think it's important to see them at work to realize how much simpler they are with respect to DGKT. So to start, you can just consider four-dimensional gravity coupled to scalar fields. When you do cosmology, this is your starting point. Typically, you have a theory of gravity coupled to scalar field, and then you study your cosmology. You have a Friedmann-Remet Robertson-Walker scale factor, which I'm not writing here, but it's implicit. And I'm also allowing you the possibility to have the space, the three-dimensional space, not to be flat, which would be k equals 0, but to be like either hyperbolic or spherical, so k equal to -1 or 1. Typically, okay, not typically, sorry. There is a class of models which is important for us now, which have an exponential potential like this, with two parameters, big lambda and small lambda. And it is known, the solution, I mean, these models are very well studied by many people. Like here, I'm citing one paper, but it's not the first paper doing it. I think among the first paper, there is Lukin Matarrese from 98 or something, I don't remember the year. I'm citing a paper we actually used eventually to also match with string theory. So this is a 4D model for the moment. And there are two branches of solutions. One for k equals 0 means flat three-dimensional space, and k minus 1 is hyperbolic. And then you have, okay, there are values of your parameter lambda here, and the scale factor it behaves a bit differently, but your scalar field solution is always of the same form, is logarithmic with time. But at the 4D level, you can have any value of lambda satisfying this bound. However, it happens that for specific values, this four-dimensional solution is a solution of an 11-dimensional theory of 11-dimensional supergravity on a 7 torus with some internal flux. I think this is also well studied, was well studied either in this paper or around the time around this paper. So we know that at least one solution of this kind is a solution in string theory, in M theory. And this is a completely classical model. There is no orientifold or other kind of higher derivative correction or whatsoever. It's just a model which in 4 dimensions has gravity and a scalar field. Now, being a solution of M theory is a good property, but for scale separation is not telling us much, because there are basically two scenarios, two possibilities. Either it is scale separator or it is not. If it is not, it's still a solution of M theory. It means it's just a consistent truncation. We cannot use consistent truncation to study effective field theories. Effective field theories means that we are safely neglecting the external space, let's say, in some sense. But we can check, so this model is so simple that we can check whether or not we have scale separation, and this will be a statement which depends on time now. It's a bit more tricky, perhaps, how to define scale separation. We propose the following: use the Hubble size. So this gives the size of the external space, which will depend on time. It's actually linear in time with this kind of solutions. And then, since we know the uplift in M theory, we can calculate the Kaluza-Klein scale, how this scale depends on the scalar phi that I showed you before. And then we turn this dependence into dependent of time. And these are the values. And you can check, it's super simple to check that if you take the ratio, they will all go to 0. So they will go with some power p, which is negative. You can calculate from these numbers. It means that the more you are at late time, which is also, I didn't say this before, but late time is the region in which you trust these solutions. Okay, don't trust this solution at very small times, because there you typically have a singularity, you don't know how to resolve these solutions. When I say they are classical, it means I'm trusting them in a regime in which time is very large. And in the same regime, I'm automatically implementing scale separation at a parametric level. So it means that even if this might have been a consistent truncation, it becomes more and more an effective field theory, more and more scale separated as time evolves. So you might say, okay, but this is just one model, you were lucky. And we showed actually that it's not so difficult to construct other models. Here is another similar proposal. We consider type 2 on 6 dimensions. Before was like 11 dimensions on a 7-dimensional manifold. Now it's 10 dimensions on a 6-dimensional manifold. With some fluxes again, I need these fluxes to generate a scalar potential in 4 dimensions. And again, the class in 4 dimensions is an exponential potential. In string theory, you typically have exponential potentials when you go for 4 dimensions. Again, we have solutions with both k equals 0 and -1. And again, the same property holds. And here there are various possibilities that we check. So we have various values of lambda, which is the parameter here. And the various values of p you can find. P is the power governing scale separation. They're all you can check that they're all negative. It means that this ratio will always go to 0 at late time. And m is the leg of the flux. So here you have 0 form flux, 1 form flux, 2 form flux, and so on. So these are all different possibilities to achieve scale separation. Okay, so perhaps we've learned something. So for sure, we have learned that scale-separated vacua in ADS vacua in string theory are far from generic. And they require ingredients like orientifolds, which we don't really understand at the level of the classical supergravity effective action. There is still the possibility that none exist. We just don't know. And I showed you that Rayleigh solutions behave somehow differently. And even though they...
Sorry, Niccolò,
yes.
can I ask a question?
Yes, sure.
Why was you get these discrete models? I mean, why did you get these discrete numbers?
Because
why is it not continuous? So what?
It's governed by this. So here I have a compactification with a flux, which is like a form field. So I have a 0 form, a 1 form, a 2 form, and so on. I can turn on this flux on the internal manifold. This will generate a different kind of scalar potential here, but it's different. I mean, the discrete choices, because I can choose to have 0 form, 1 form, 2 form, and so on. This will turn in a different scalar potential, meaning a different lambda. And then lambda governs here the profile of phi and also of the scale factor here. So I have discrete choices of lambda, which are governing phi and the scale factor, meaning phi will govern eventually the Kaluza-Klein scale and the scale factor the Hubble. So this is why a discrete possibility.
Thank you.
Okay, so as I was saying, Rolli solution, even though, let me say this is very preliminary, but it seems that they behave differently. I showed you very, very simple examples. Maybe they will turn out to be inconsistent, but for the moment, we don't see any inconsistency because also we are really working with classical ingredients, like really supergravity approximation. So we think that it's a strong hint that scale separation in vacua, in solutions which are rolling solutions that are not vacua, might be more generic than on vacua. And also a more pragmatic message that we learn is that, so I showed you two examples that work in the sense that they have scale separation. We also tried something a bit different, and we tried to generate scalar potentials, not just with fluxes, but with curvature of the internal manifold. And in that case, we couldn't find scale separation. So perhaps there is an obstruction here also to learn. We don't know yet. But the models I show you are all with richly flat internal space. So to conclude, scale separation is a minimal requirement for phenomenology in theories with extra dimensions, like string theory. And it's a kind of an hierarchy problem for the universe. And as any hierarchy problem, it's challenging theoretically. So we have to explain why we see very, very small numbers or very, very large hierarchies. And we have to explain from first principles, and we don't know what are these principles. And one of the things I would like to stress is that in the recent years, there has been, I think, really remarkable progress in this problem. And among the other problems I'm familiar with, I think this is one of the problems in string phenomenology in which there has been the most progress, I would say, because only in 5 or 6 years, I showed you the paradigm has changed completely. We were able really to rule out the vast majority of the theory space in models, at least with supersymmetry, using combination of different ideas, which for the moment, they don't seem to clash, okay? So I was using weak gravity conjecture. I was also using entropy bounds, which are in some sense a manifestation of holography. And all of these ideas are different. In principle, they are independent. But for the moment, we don't have any clashing between them. We didn't find the case in which maybe weak gravity was ruling out a vacuum which was supported by other arguments, okay? For the moment, everything seems to be self-consistent. And also there has been constructions, and there is still today constructions of new models from 10 dimensions. And I think this is also important because up to 2020, we basically had one model to work with. And you can imagine that having just a single model is making life hard if you want to understand general properties, because you have to play with that model. And if that model is hard to understand, you are stuck with that model. Having more models with different ingredients and different behaviors, I think is much better for us. It allows us to make progress more in a better way, I would say. And this is only about vacua. So today, I think we have ordered 10 different models, more or less. And this is only about vacua. We have still to explore the whole problem of scale separation outside vacua. I showed you preliminary results, but I think it's very promising. And I think several questions on scale separation are today likely within reach. So thank you for your attention.
Any questions for the speaker?
I can ask.
Yeah.
So Niccolò, can you hear me?
Yes.
Okay. So I wanted to ask if these rolling solutions do not have the interpretation of being separated by a domain wall, right? Or do they? Because they're not expanded.
They're not vacua. Yes.
Yeah.
So yes.
They
I would say no.
They evade your domain wall bound criteria at all. Right?
The domain wall bound I showed you before was for vacua.
Yeah.
I derived it on vacua, really assuming vacua. So I don't know what happens outside vacua for that. Okay, maybe there are some studies which I'm not aware of, which I just don't know personally, but maybe like the covariant entropy bound for sure has been studied outside vacua. I just don't know personally. But yes, the derivation I showed you before was for vacua, and I don't know immediately how to one has to study from outside vacua. I would have to study it. Yes, I don't know immediately.
Okay. Also, one more question. So for D equals to 2 scale separated solutions, there was
Yes.
also, in your first graph, there was a possibility of having one supercharge, right?
Yes. Yes.
But the explanation that you gave for ruling out of all the other supercharges was the tension of the brain should be higher than the UV cutoff, right?
Yes. Yes.
I mean, why is one supercharge not included in that case?
Why? Because in this argument, what is it? 1 second. Yeah. Here I need the domain wall to be BPS with respect to the one. Sorry, I should have said 1/2 BPS with respect to the two-dimensional theory.
I see.
It means that this guy should preserve 1/2 of the supersymmetry of the vacuum. I can have 1/2 of 2 supercharges, which is 1, but I cannot have 1/2 of 1 supercharge. So I cannot say anything with vacua with 1 supercharge because I cannot construct a BPS domain wall interpolating them. But I can say it for 2 supercharges or more.
Okay. Okay. Thank you.
So I have one remark and 2 questions. So for the specific method, can you hear me?
Not very well, but okay. Try. Maybe I'm able to understand. Try nevertheless.
This is better.
Yeah. Yeah. So I have one remark and 2 questions.
Yes.
So one is for the specific metric ansatz that you took in your paper in this rolling solution.
Yes.
We actually constructed an explicit time-dependent background for that with all of the type 2b fluxes in.
Okay.
And in that, we also showed, for example, if you have how to evade the Maldassena-Nunez in a non-trivial way.
I see. Okay.
So in the original formulation of the Maldassena-Nunez, they were taking certain kinds of flux choices. That is, either you have to have legs of your flux in the non-compact spacetime, like covering all of the legs, or none of them. But if you relax that assumption, you actually get around the obstruction as well.
Okay. Yes, sorry, I was not aware. I'm not, I mean, rolling solutions are not really my field, so I'm not aware of much of the literature. And I'm sorry. Actually, if you can send me whenever you have time in the paper, I will look at it.
Sure. So, well, we haven't checked the scale separation in that work, but yeah, that's just.
Yes, I mean, let me stress, for sure, the solutions I showed you are known already. What we think was not known is that they are scale separated. It's similar for the vacua story. The M-theory vacuum I showed you. Okay, no, the M-theory one, the massless type 2A vacuum I showed you was known already before by people in 2006. It was not known that it was scale separated. This was our original contribution, let's say, not the vacuum itself, or not the rolling solution itself, for sure.
Yeah. Okay. So I have one question. So can you go to the slide where you were presenting the model after DGKT, your paper? So DGKT had an obstruction to tuning the F2 and F6. I think they were tuning the F4. So how? Yes. I'm a bit confused how you got around that.
I mean, the shortest answer is that you do 2T dualities. So you turn the obstruction into an obstruction for other guys, but not this one. So there is F2. I think here I have a typo probably because these are the same, but they should not. I think this should be 2,2. So this means a certain component of F2, let's say along the first torus. And I think this should be like the second or the third torus, I don't remember now. So F2 has 3 or more components, I don't remember. Some of them are constrained. I'm not showing them here, but there are 2 of them which are not constrained. And these are the 2 I showed you before. I mean, the obstruction is just because the model is different, okay? The tuple is different, and the way the fields enter the tuple is just different. There is nothing deeper than that.
I see, okay. And I think you commented in this paper about some obstruction with the dark dimension scenario. Can you maybe say?
Yes, I didn't say this because I don't know. So I didn't know how much of the dark dimension scenario was known to the audience, so I didn't want to spend time into introducing it. So the idea of the dark dimension scenario is that perhaps the size, more or less the size. What we showed is that in this paper.
Sorry, you're breaking up. No, we can.
Our internet seems fine.
Can you hear me?
Yeah, yes. Now, yes.
Okay. Yes, so what we showed in this paper is that if you use the covariant entropy bound, which is, where is it again? Sorry. This kind of bound, and you impose it on the dark dimension scenario, assuming it's a vacuum, you basically, you can rule it out under the assumptions that the UV cutoff is the 5D Planck scale. So you cannot construct an effective field theory of the dark dimension with UV cutoff the 5-dimensional Planck scale.
Also.
With one single, there is a caveat, so you cannot construct a theory with one single extra dimensions, okay? You can understand, you can put a bound actually on the number of extra dimensions this way. So the way we did it is that you can relate the ultraviolet cutoff to the number of extra dimensions which are decompactifying. And there is a formula to do it, which is heuristic, but for the moment, we believe it's more or less correct, at least in the approximations we're using. From that, so we have a parameter now, which is the number of extra dimensions. And you can see that depending on the value of that parameter, this bound is violated or not in the dark dimension scenario. And it turns out that you need at least two, if I remember correctly, 2 extra dimensions for this to be satisfied, if you use this assumption. So strictly speaking, the dark dimension scenario with 1 extra dimension, which is the original proposal, is ruled out if you under these assumptions. It might be not a vacuum. Maybe, I mean, I think the most likely possibility is that eventually, if it is correct as a scenario for our universe, is not a vacuum, and then okay, I'm ruling out the vacuum possibility. Or you can use a lower cutoff, and then you understand that if you lower the cutoff, you are going in this direction. So if maybe the bound was not satisfied for some cutoff, but you push it in this direction, it maybe becomes satisfied. The other logical possibility. Yes.
Okay, thanks.
No problem.
Also, I have another question. So just a remark, not a question. Tell me if I'm thinking it correctly. So this domain wall bound can only be used to test supersymmetric vacuums.
Yes.
So like you mentioned that all of the supersymmetric scale separated solutions, after flipping, possibility of flipping signs of fluxes, you can have some non-supersymmetric ones as well.
Yes, right? For that we cannot say anything. Yes.
Yeah.
Precisely. For that, I mean, I don't think there is really any objection. The only thing people typically say about non-supersymmetric ADS vacuum is that they decay, right? Because they are non-supersymmetric, so they are not stable. Mm-hmm. But I think then this doesn't mean, in my opinion, that they are not good solutions. It just means that okay, it depends on the decay time. Then, if the decay time is sufficiently long, maybe you are able to do phenomenology, or once you go to the sitter, you are able to do phenomenology out of them. But you're entering different kind of questions then. But yes, this bound and all of I said here was using supersymmetry.
Right. So this bound is a kind of a string theoretical way to think of the black hole bound that you showed, right?
Yes, precisely. Is okay. So we used supergravity, still 10-dimensional supergravity. So it's a bit classical still, the reasoning, but yes, that's the spirit.
Right. So the non-supersymmetric vacuums can still be tested against those black hole-like bounds, no?
Yes, if you believe those, yes.
Okay. Cool.
And let me see. I don't remember if we checked them actually. Probably we didn't. I mean, I think I can say probably. I think this will be true again. Probably. Okay, I think we didn't check, but I suspect that they are going to be satisfied again. Here, here I talk about KKLT, which has a supersymmetric anti-de Sitter vacuum. There is another scenario which is called LVS, a large volume scenario that has a non-supersymmetric anti-de Sitter vacuum. You can test the bound on that vacuum, and it was satisfied. Okay, let's say you are agnostic about the derivation, as you said. You just take the bound from the literature on black hole entropy bounds and whatever. You test it, and it was satisfied for LVS.
It was satisfied for LVS.
Sorry?
It was satisfied for LVS.
Yes, for LVS, yes.
Okay.
Okay, cool. Thank you.
No problem.
Okay, let's thank the speaker again. Is there any more question? No? Okay, let's thank the speaker again.
Thank you.
Bye. Thank you for the talk.
Thank you.
Bye. Thank you again for the invitation. Bye-bye.
Bye-bye.
Bye. Okay, bye.